Okay, so we left off doing sums with evenly spaced rectangles, and today we are going to introduce Reimann sums, which is a new kind of sum. It's a kind of weird looking name, but the only difference now is that as we sum our rectangles, we are not going to force them to be the same width. Okay, so by definition, a Reimann sum is when we take the sum over an interval with rectangles of unequal width. So let me kind of show you what that might look like. So here's our function, f of x, and as we want to find the area, let's say under the function from here to here, okay, so from A to B, instead of forcing each of our rectangles to have the same width and be regular, we might pick them to be different sizes. Okay, so notice this last one's a lot bigger, middle one's kind of in the middle, and then the first one's smaller, which, oops, sorry, first one would be here. Second one would be here, and the last one would be here. Alright, so we use that to make our approximation. Okay, so we're going from a sort of specific thing of finding the sum of rectangles of equal widths to a more general scenario where they are unequal widths. We will find ultimately that the equal width rectangles are easier to work with, but we need to understand this idea of unequal widths in order to sort of make our final proof of finding areas exactly. Okay, so let's try the mechanics of this with example 1. So we have the region bounded by the graph of f of x equals square root of x, and we're looking at the area between x equals 0 and x equals 1. So at 1, y equals 1, and we want to evaluate this limit. Notice, okay, one major difference here. Okay, before we dealt with delta x, now we have a delta xi. So now that we're dealing with Reimann sums, the widths are not necessarily the same. That means that instead of just having one delta x, we need to have a delta x for every rectangle. So we notate that with delta xi. So looking back at our example up here, this one, the width would be delta x1, the next one would be delta x2, and so on. Okay, so delta xi is what we're dealing with now. Okay, so back to example 1. We've got square root of x drawn. We're looking from 0 to 1. Let me go ahead and draw in this area so you can see it clearly. This is what we're trying to find the area of. Okay, and instead of using a regular set of intervals, we are going to call each right endpoint using this, ci equals I squared over n squared. Okay, so our endpoints are given here by this expression rather than finding ci using our previous methods. We're given the ci. Okay, so the first thing we need to do is find what delta xi is. And probably the easiest way to do this is to, let's go ahead and draw a couple. So you'll notice since ci is a function of I, as I gets bigger, okay, ci gets exponentially bigger because it's I squared. So as we move to the right, okay, our rectangle's widths should also increase, okay. So think about it. If we want to know the width of the first rectangle, okay, the width of the first rectangle, okay, if the right endpoints are ci, so that would be c1, c2, and c3, okay, the width, which this would be what we would call c0, would be c1 minus c0. There we go. For the second one, it would be c2 minus c1, and so on. So for the first rectangle, it's the actual right endpoint of what you're starting with minus the previous right endpoint. So we're going to write that in a generic way. So it's ci minus ci minus 1. Okay, so writing that in, given what ci is above here, this, it's I squared over n squared minus, parentheses, I minus 1 squared over n squared. Okay, so let's solve that really quick. It's going to be I squared minus I squared minus 2I plus minus, let's see, I'm sorry, this one should be a plus, and the last one will be a minus 2, all over n squared. Okay, I squared cancels, 2 can factor out, so we're left with 2, I minus 1 over n squared as our delta xi. So whereas before we had a nice simple delta x that did not depend on I, now delta x does depend on I, so that's going to come into play when we're doing our sum. Okay, so now let's go ahead and set up the sum. Okay, and again we're looking at the limit as n approaches infinity of the sum of f of ci times delta xi. Okay, so we'll set that up down here. The limit as n approaches infinity of the sum from I equals 1 to n. Now f of c is square root, so we're just going to take the square root, and then again ci is I squared over n squared, which, that's awfully convenient. And then we're going to multiply by delta xi that we just got here. So 2I minus 1 over n squared. Okay, so now simplifying, approaches infinity, sum I equals 1 to n. The square root is going to turn this into just I over n, and then we've also got this n squared here. So n times n squared on the bottom will give us a 1 over n cubed. Out front, that's a constant. And then inside here, we're going to be left with what? Let's see. 2I squared minus 2I. Look good? And that's it. Okay, and our n cubed is out front. All right. Now that we have everything in, we can use our summation formulas to simplify and get our final answer. I'm going to let you take a look through the book to get all the final details, but we find that our final numerical answer is 2/3, which is actually pretty interesting because if you remember, we looked at a function that was f of y equals y squared, and we found the area from 0 to 1 in the last example of the previous lecture, and that looked like this area here, okay? And we found that area to be 1/3, okay? So this area that we just found here is 2/3. You add them together, you get 1, which is exactly what you would expect because it's a 1 by 1 square.